my simulation runs, it's a demo example, something simple. It uses 9 processors. We can see it here. I run it with MPI exec 9. And it runs 100,000 iterations, and it stops. OK. So there is the challenge. I have a simulation, and I'd like to connect my visualization application to it while the simulation is running. So here's how I do it. I will first show you the demo, and then we will talk about the library itself. There is my simulation running again. For the purpose of the demonstration, it's waiting now, because otherwise I'm talking and then the thing finishes. It's a demo example. It doesn't last very long. It lasts, yeah, a couple of minutes. It's a 2D simulation program. That simulation is running on Castor. Castor is another cluster here at CSCS. I just put it there because I didn't want to make Iger do any additional work, etc. I will launch Visit on my laptop using the same technique we used to connect to Iger. I have a host profile for Castor. I will connect to it, open Castor, password, that's good. There we go. Wait a second. What file am I supposed to open? There's a simulation. It doesn't write any files, any solution to disk. Not quite. It writes a little file, 4 lines. We could actually see the content of this file. It writes the following file in the .visit directory, subdirectory called simulation. It writes this file called temp.sim2. And what does it say? It says that there is a host called Castor12. This is the node that the batch system has given to me. And it has a password. Visit is going to read this, use that particular password to connect to the simulation. This way, nobody else can connect to my simulation. This would not be very private. There. At this point, I'm connected on Castor number 12. You can see, can I stretch this? There we go. I'm connected to Castor number 12. There are 9 processors here. And this is the command. As I connected myself, the simulation has given me the metadata about the simulation. So Visit now knows that there is a file, not a file, there is a set of data with the following characteristics. A mesh called mesh with 9 blocks, because I'm running with 9 processors, so 9 distributions of the domain. The domain is 2D. Okay, it's very simple. And the rest is at the bottom of my screen. We can't see it. There's a field called temperature. I'm going to visualize the temperature data like this. I told you that the simulation is waiting to start before I connect, such that I have time to explain to you what is going on. And now, if I go to my simulation and say run, it will run in the background. And when I say update, there it is. And update again, there it is, and so forth. I can restart and update. I can interact with my simulation. In the meantime, see, this is my job on the cluster here. It says every node got connected, and they wait for commands that visit is given them. All right, this is not a crash. Trust me, this is just the fact that I got to the end of the 100,000 iterations. I will, do I need to restart it? Yeah, I will. I will restart it. So I will reopen. Because I have some other things to show you. Yeah, questo me l'aspettavo. This is not connected. Compute. I think I do much better at quitting the client. There is visit. What I want to point out is the fact that I do not have to think about any particular visualization technique I want to use on this simulation. So I don't need to have a pre-assembled visualization pipeline. Anything Visit is capable of doing, I will be able to do with the running simulation. Somehow I cannot connect to Castor anymore. The file open doesn't react. So I will go to my presentation and we'll try again later on. So this is in-situ visualization. We'll talk about the following things. Different ways of doing in-situ processing. The LibSim library, which is visit-specific. How do we enable this in a running simulation, and the source code? Now, people are talking about, well, petascale, not anymore. Exascale, and they say, oh, it's going to be impossible. We'll have millions of cores. We're not going to be able to do I/O, which is true. We need a solution to interact with our data. We need to do in-situ analysis, to do online data reduction. So before saving data to disk, we need to do some visualization to reduce the quantity of data we save to disk. Of course, there are requirements. It needs to have a low memory footprint, being scalable, and all this discussion. Of course, here I put the discussion in terms of very large-scale simulation, but I would actually like to encourage you to use this just to debug a particular simulation. So debugging, usually we do this at low scale, and it's perfectly doable. When we have too many cores, too big a grid, usually this is what we do. We undersample the data we save to disk. We skip many time steps, etc. And the problem is you visualize data on a supercomputer, you dump it to disk. I cannot use my small visualization cluster to visualize the data. I have to reuse the supercomputer to visualize the data. Why not do everything at once? That's really the motivation for doing in-situ. Here are some actually old numbers, the latest being from 2012 on the ASCII Sequoia machine. doing what do you call it, a whole system checkpoint, uses 0.001% of the total writable flops, and it takes over 3,000 seconds to save the content of memory to disk. So very, very difficult to do I/O on those systems. This is a case which I have run here on Rosa, actually. You can see here the file name. The host name is Rosa, running on 3,200 processors. I was reading this data, and I went out to drink coffee, and I was still reading the data, and this is what I see most of the time. I'm waiting for processors to do I/O. This is unbearable. Here's how we can get around this problem. Either read much less data, use multi-resolution techniques, use wavelets, use other ways of reducing the data, using on-domain streaming. On-domain streaming would be just like viewing YouTube videos. You never actually have to download the full file. You can just watch it as it goes through. This is streaming. This is called data streaming. It's implemented very well in the VTK library. What's missing is the visit and ParaView using this low-level library to do streaming. There is some efforts in ParaView to do streaming, meaning only reading a little bit of data, processing it, then going to the next bunch of data like this. But it's difficult to exercise. Other solution is to do in-situ. So doing in-situ, we can eliminate all the I/O to disk. Magically, we don't have to worry about ghost cells because the simulation holds the ghost cells. So it's there already. We don't have to worry about this. We have access to all the time steps. Well, not quite, because the simulation runs. If you ask me for the time step 10 iterations before, it doesn't exist anymore. It's not in memory anymore, because the simulation will presumably overwrite its solution time step. So this will be one limitation of the solution. We'll use the original computer allocation, so this is very good. We are able to start an in-situ session, quit, reload it at a later time in the simulation. All of this is possible to do. And that will allow us to do, of course, debugging and computational steering. Multiple ways, multiple techniques have been used to do this. The so-called loosely coupled or concurrent processing. This is where we use one supercomputer and another supercomputer or cluster connected to it via wires, and we send the data over the wires instead of to disk. It requires quite a bit of work in terms of resources. There's the tightly coupled co-processing paradigm where we bind together simulation and visualization. This is what we've implemented in Visit. And then the hybrid solution is the case where you would do some data reduction on the supercomputer and send that to an additional resource elsewhere. Yes? Yes. Yes.
Well, we just use one CPU core to actually send out the kernel.
Yes.
So we have 7 cores doing nothing.
Yes.
So would it be possible to use these 7 cores to
Absolutely, it would be. It would be.
Update the memory?
Yeah, yeah. There is actually a project called Damaris. It's in France at INRIA. This is a co-project with INRIA and Oak Ridge National Lab, where they have done such coupling, where a subset of cores on the node do simulation, a subset of cores do I/O, a subset of cores do visualization. So this is a perfectly good approach. While you are talking about GPU, let me make a parenthesis. Can I use GPUs for the visualization on Daint and Scientist and those machines we have here, those supercomputers we have here with GPUs? The answer is no, unfortunately for the moment. Take a code like Visit. There's more than 1.3 million lines of code in C++. There's a huge effort that needs to be, and that nobody is ready to pay for, that would have to be done to go to the GPU. There is an alternative approach. Instead of using GPU, is to use multi-threading. So it's hybrid programming, MPI, and multi-threading on the node. This I have used already and benchmarked. It's very promising. It's not a full data programming type of operation, but it's actually a very nice speed up using far less MPI resources than available. So the case you mentioned, using GPU to do the computation and using the unused CPU on the node to do visualization, would be perfectly applicable to using multi-threading parallelism on the node. It's not production ready, okay? I've had to do quite a bit of hacking to make it work here. But I had some good benchmarks, and I'm working with the people at Oak Ridge to make it more reliable. Loosely coupled, we would be doing this. Simulation and I/O layer, probably some kind of a network boundary, saving data to a memory buffer, reading the data into a viz tool. There's a lot of copying and moving data here, and it does require a separate processing resource. It has its pros and cons. In this case, yes. There are colleagues of mine here at CSCS who have implemented that using an HDF5 interface. The simulation thinks it writes data to an HDF5 file object, but using the virtual file layer of the HDF5 library, the data is actually sent over a wire to a connection on another computer. Okay, this is a project of my colleague John Bidiscombe here in the group of Professor Schultes. The principle is exactly this. Yeah, you make the simulation think it's doing I/O, but it's not doing I/O to disk. There are cases where visualization has been embedded directly into the code. For example, many of the persons I work with in Zurich doing astrophysics. Astrophysics are the big consumers of CPU and I/O and everything. They write custom visualization code into their simulation because they just cannot afford to save the huge quantity of data. This is good, it's very efficient, but it's exactly this type of problem. You write it once for astrophysics. If tomorrow you give me a geophysics code, I have to do again the same effort. So it's not very portable. What Visit proposes is a data adapter layer. the simulation writes to this data adapter. So it is an avatar. The simulation thinks it's writing somewhere to a disk. And then we use the visit engines, which means we can do all the different visualization techniques we've seen today and more, because the data is there available as grid data. This is the approach that has been used. So the library, which is this data adapter, was written once, but then we can have multiple simulations use this particular interface. From the point of view of the user, you've seen it already when I was showing you the 2D heat equation solver. It looks just like the standard visit. Visit doesn't know the difference except for this particular panel, which shows the run, step, hold, and whatever menu you want to add to the interface. Here's how it looks like. The simulation has its data. The visualization server, so the engine server of visit, is embedded into the MPI tasks. And now the visualization pipeline can be implemented on that data in memory. How do we do it? It's usually, so first of all, LibSim, which is the name of the library in Visit, is an integral part of Visit. There's nothing you have to compile additionally as an option. It's there. When you download it, it's available. It uses a small front-end library, which is very light, 70 kilobytes, I believe, which is linked into the simulation. And at this point, the simulation can run already. We don't have to actually connect to it. So it's a very small weight which we add to the simulation. If we want to connect to it, well, we write the data access code, and the simulation can run. When we connect to it, and only at that time, the runtime library of the visit engine is loaded in memory. And the data can flow through the visualization pipelines. What is important is that this library acts on demand. This is really why I do not have to specify a particular pipeline before I start connecting to my simulation. It gives me complete freedom to interact, to debug my code by looking at whatever field is available. Here's how I would work. I would launch the simulation code. At regular interval, the simulation checks to see if there is a request for connection. If there is a request, we establish that connection. At that moment, the simulation advertises what data is available. So Visit knows the shape and size and number of grades and variables, etc. And at that point, I can start requesting visualization services from the simulation. Additions to the source code. It takes 3 incremental steps. Do some initialization, and this is about 30, 40 lines of code, which we cut and paste from all the different demonstrations. It's the same initialization, nothing fancy here. We have to make sure there is an iterative loop somewhere. Otherwise, if your simulation is just one thing, maybe very long, and then it quits, there's no iteration, there's no chance for the visualization to connect to it. Because we need a point where the simulation returns frequently so that we can check this feedback with visit. We create the data access callback function. This can be done, by the way, in Fortran, in C, and in Python. The example I'm presenting here is on the web for everyone to try in those 3 languages. What is a data access callback function? It's providing a pointer to the data in memory which visit can use. If it's a pointer, if it's a scalar field, it can be very simple, so that callback can actually be a dozen of lines of code, and that's it, just passing the pointer in memory. If the data is organized in a more esoteric way, we might have to do some reshuffling of data to make it compatible with the VTK data organization, because remember that visit is based on VTK, so internally the data structure are VTK objects. And then we add some controls, just like those couple of buttons I had to start and stop and single step through the simulation. Those are graphical user interface control which are hooked up to the simulation. There is the case, the standard case. This is your simulation. It gets initialized. It does something, astrophysics, geophysics, biomechanics, whatever it is. It solves something. There is probably some check for convergence, end of running, whatever. And if not, we continue. This is your normal execution path in your simulation. And here's what I do with the visit library. I insert in the middle this visit, detect, input. This is about 40 lines of code, which is cut and pasted from the examples. It's application independent. This is to say, I need to control if there's a request for connection. If so, I connect. I need to get the name of the commands which visit is requesting. If visit is asking for an ISO surface, that command is passed and is processed over here. This is optional. Let's skip it. If so, I process the command, and then I return to the simulation, which goes to the next time step. And as you saw in my demonstration, the simulation actually finished early, so it just quit because I had nothing else to do. So the simulation really is independent when visit doesn't do any intervention with it. The font here is really weird. I don't know if you can read it. This would be an example of a data callback. This is my simulation. It has an array of size 6 by 8, a scalar field called pressure. I have a pointer in memory. My callback is like this. If visit is asking for a display of variable pressure, I get a handle. I allocate nothing, actually. I pass the pointer in memory, and I say, and I give it this special flag, visit owner simulation. The simulation owns this particular memory pointer. What does that mean? It means that visit has no right to override the data, so it's read-only. And the other thing is that the simulation is responsible for the allocation and deallocation of the memory. So everyone knows what their job is in terms of memory allocation and so forth. What can be done? Any data type which visit supports already today can be provided by the simulation. So all those different things we've seen as examples. Yes? Yeah. Okay, okay. What is the second question? Yes. Yes. Yes, it is. Okay, so first question, nothing prevents you from still doing I/O. So I recommend you also do some I/O in the debugging phase. In fact, even if you run a very large-scale simulation, at the end, probably you want an I/O. You'll do I/O just like normal. This is an additional functionality. Second case, can you ask the simulation to watch for a particular event? The answer is yes. You send it a string of Python commands, and you say, simulation, wake up. If that particular condition is true, do something, save an image, or whatever. So that has been tested. Is it reliable? You were asking me. I've run it on Rosa on 16,000 cores. This was done during the maintenance benchmarks of Rosa to make sure. So we run it as big as we could, and it was just running fine. Of course, there will always be the counterexample. It will crash at times. So continue to do some I/O. This is the minimal graphical user interface that I would provide. A button to do halt, step, run, etc. And then I can add more buttons. And I can add some specific graphical user interface widgets to link to specific parameters of the simulation, such that at the next step of my simulation, I can modify the parameters used by the simulation. So this is an initial form of computational steering where we modify the behavior of the simulation. Oh, there's the example here. We have on the web this particular example of an adaptive mesh refinement where we change level of refinements and refinement ratio through the particular GUI. Those are from an example of simulation I had done in 2010. So this has been going on for several years now. As your simulation calculates, you can save different snapshots, etc., of data. What is the cost of it? At every iteration, I check for visit, and what we have measured using 512 processors was the cost was 2 microseconds. I think you can afford that, 2 microseconds. What is the cost in memory? That's a little bit more expensive. At simulation time, 8 megabytes, independent of the size of the job. After initialization, another 8 megabytes. And after loading visit, 200 megabytes. It's getting to be a little bit fat in terms of memory. Fortunately, visit, you probably see it on your computer. Visit is made of hundreds of shared library objects, which are loaded when you start visit. So the one optimization is actually to get rid of all the things you don't need. For example, if you're never going to do an isosurface, you don't load the isosurface shared library, and so forth. So for a specific application, you could reduce the set of features you need to a predefined list and load only those shared libraries. Here's a benchmark I've done. There we go on Rosa, using all the way to 16,000 cores. For this simulation, which looks like something it's done in purpose, This is the grid used for weather simulation. Size of the grid at this particular number of cores was 20 gigabytes. The I/O I could do was 2.56 gigabytes per second. So my I/O climbs like this in a linear fashion. So does the processing of this particular task, which was to do 10 isocontour threshold. But as you can see, the difference in time is only, let's say, 8 seconds for 20 gigabytes of data. I could never read that much data. I could never write the data to disk and read it back into my visualization as quickly as this. If now I change the size of the block per core, I would get to a total size, file size of 140 gigabytes. And this time, the in-situ visualization wins completely. This is my scalability time for the in-situ visualization. And this is the cost of doing I/O to the file system. The advantages are the following. The bottleneck of I/O can be avoided, not eliminated. You can still do I/O if you wish. There's no more discussion about file formats and is it supported, is it not supported, is it parallel? No, it's there in memory. It works. No file formats discussion. No ghost cells reconstructions required. All variables are available, even the ones you don't usually save, the temporary files, which can be very useful for debugging an application. They are there in memory, so you can display them. Limitation for the moment, it's still memory intensive. Runtime library cost is larger. Static linking is difficult to do, but we are doing this already. Zero copy, which means the possibility to sharing a memory pointer between the simulation and the visualization, works very well in some cases, but not all. You know very well, you write simulation code. Sometimes the access patterns of your data in memory is not linear, etc. There is something new. In VTK version 6.1, there is a class called VTK mapped data array, which has been designed exactly for the purpose of doing in-situ visualization so that you can match the memory footprint of a simulation with the requirement of the visualization application. This is an activity funded by the Department of Energy in the States exactly to develop in-situ visualization code in a more effective way. So there is clearly interest for it. This is from the presentation we did last year, so it's not true anymore. We don't actually need an interactive session anymore. We can run a batch connection as well. Here's the example, and that example is on the website of Visit in Fortran, Python, and C. In this particular case, I run it like this on Castor. This is an initial time step, and then as the simulation go, we have convergence towards a certain solution. We've seen how this is done. The host profile is written to a very small file, which Visit reads to get its connection information. This is the Visit library, which I know very well because I contributed to it. ParaView has something similar called Catalyst. And I've tried really, really hard to make it work. It's not simple. It's convoluted. I think they both have merits to be followed. And the paper we presented is also available at this website if you want more details. I will attempt one more time to connect to this because I had some interesting feature to demonstrate. All right. This is it. We are starting here anew. There we go, I'm connected. See the difference here? When I open my file, it doesn't ask me how many processors I want anymore. It already has the processors, all right? So earlier I showed you a pseudo-color map of temperature, which was this. And this was my initial configuration. If I run a little bit of time, and I hold, there is my data. Of course, I could show you the grid. There is something I could show you, my ghost zones. There we go. This shows the distribution of the MPI job for this particular grid. So this is a 2D Cartesian decomposition of the domain. Let's delete all of this. Let's show a histogram of my temperature data. 256 to make it a little bit more interesting. There. What do we see in this particular graph? We see that we are at the iteration number 1175. If I run again for a little bit of time and hold, I will update my, see now I'm iteration 2000, etc. I will run and update, etc. So what does that mean? I have really freedom to do anything the graphical user interface allows me to do. However, by design for this particular demo, here I'm talking and the visualization is sitting, doing nothing, because I want to be able to have time to explain things. Under regular terms, you would not hold the simulation. So the simulation should be allowed to continue running. There, so let's go back to my plot of temperature. And I think I have, let me check if I have an option to, no, not on this particular demo. I can only update when I stop the simulation. Updating the graphics for every time step would certainly be too expensive. So we don't do it by default. Now, you are debugging a simulation. And trust me, I actually had to debug this demo to make it work correctly. You are free to inspect the data as you wish. So here's my pointer. If I see here that the graphics has something wrong with it, I can click on it. And this is my information. I am on the MPI domain 3 at position X, Y, like this. This is zone number 5600. Here are the values of my temperature at the 4 corners of this particular cell. So there I have, in my mind, well, it's not better. It's complementary to a debugger. In a debugger, you can go look at the execution of your different subroutines, etc. You can inspect numerical values. Here you can inspect numerical values graphically, or using some of the data analysis techniques like we did this morning to get some quantitative analysis out of it, and then you can understand which MPI, which task is doing the wrong simulation, whatever that is. So there, I am done with this. I can let the simulation run to the end. In fact, it has run to the end because it shows here an empty domain. There. This is a toy demonstration, but this has actually been implemented on real codes. When we published the paper, we implemented that. We coupled this with a real astrophysics code, and we demonstrated it running on several thousands of processors. My colleague in the States have this running now on new codes, and this is a really viable way of doing computation. It's there, it's open source, which means you have the source code. You can look at the examples, you can test it. You can start implementing that into your simulation if you wish to have that particular feature. Once you have the code instrumented, you're not obligated to connect, to visit, to run your code. You can still run your code in a normal way. So this could be done as a single diagnostic once in a while, such that you don't waste computing time. You can check the live status of a simulation to make sure things are doing the right things. Then you disconnect and you let your simulation continue its normal job. Yes? To get which kind of output? What you can do is send a full. You could send a small Python program as commands to the simulation for it to update certain files on a regular basis. So you could dump some particular variable output, some particular images or numerical results to some diagnostic files. Yes, you can do that. There we go. So 2:30, 3:35. Any more questions about this? No? Okay. All right. So we'll stop with this particular demonstration. Is there a particular topic that I need to revisit with you over the multiple things we've attempted to do in these last 2 days? This is a good time to try to nail it down. Yes, no. Difficult. There's a lot of stuff that. Yeah, this is good. Yeah. Yeah. Very good. That's a good case. I prepared some slides for a tutorial I did before Christmas. I think it's right here. Yeah. Exact. I believe so. Why should you prefer ParaView or Visit? That's your question. There are examples like this. Transit data. ParaView has a comparative viewer where you can actually plot. I mean, you need to have a big screen. This is done for the people at the national labs that have those gigantic screens where you can show multiple time steps next to each other in different windows. Actually, it works, but it keeps all the data in memories. It's very expensive. It's there. In practice, I don't think it's used very often. This is an advantage. However, ParaView has no language structure like we saw this afternoon to do time step based operation. So averages, comparing, differencing, etc. between multiple time steps. I told you that ParaView has this very strong limitation that at the exception of the comparative viewer, everything else is fixed to a given time step in the ParaView pipeline. Then you'll have cases like a particular application. NEC 5000 is a solver developed at Oregon National Lab. Visit as a direct interface for that particular output. So here, there's no question, there's no alternative. You use Visit. Okay, querying. Here's an example that I kind of like. The people of Kitware are angry that I show this, but it's true. In Python, if you use ParaView, if you want to get the minimum and maximum of a scalar field, what's the command? The command is this: get active source, point data, get array, pressure, get range. It took me about 5 minutes to make it work correctly. If you do the same in Visit, you type query min max. Which one is simpler? I'll let you decide. Binning. This is something I have not had time to demonstrate in Visit. It's unfortunate, but you can go to the wiki. In fact, I don't know how much time you want to be here this afternoon, but I could do a quick demonstration of binning. What is binning? Binning is a way of sampling your data at regular position in space. Those positions can be programmed, and on those sample data you can do operations. For example, you can do an average, you can do a probability density function, etc. So this is a full toolkit that is available in Visit. In ParaView, you can do it, but it's exactly similar to the in-situ visualization option I presented earlier. This is the case where if you give me some geophysics data, and I have done it exactly for that purpose, I can write the solution in Python and do. In the case of geophysics, I had to do a longitudinal average of data. Seems like a pretty trivial thing to do. Not so. You have to program it in ParaView. Whereas in Visit, I have a graphical user interface for the tool, and I ask for my longitudinal average. So there's some difference. Particle data, gridless. Visit as, okay, both Visit and ParaView can read the so-called H5 part reader, which is an HDF5 convention for particle. However, Visit couples this with the fastbit library, which is a library done to do query indexing on very large. Here I'm talking about billions of particles type data set. in a very, very efficient way. So this would be a clear advantage of using the visit solution. Rendering, ParaView as better rendering because ParaView and VTK are done by the same people. So they know better how to use the VTK toolkit to do rendering. I'm going to try to show you this. Those are two examples of enhanced displays, which I like very much in ParaView. We'll get to this. D3 is a mesh partitioner or repartitioner, which I use. It's not extremely robust, but it exists, whereas Visit doesn't have any. There are differences in data format. I've given examples already. Pipeline management. Visit is much more compute conscious. I've given you a whole explanation about the execution model of the pipeline. In ParaView, you load your data, and automatically it makes a display of it. Then you add filters, and it re-executes the pipeline. And you keep adding, and it keeps re-executing this pipeline unnecessarily. Whereas in Visit, set up your pipeline all the way to the end, and at this time only the data is loaded in memory. So this can be quite a difference. Cumulative queries. I have a great example to show. Let us decide if we have time, if you want for me to look at this demonstration. Cumulative query, I don't know if I explain here. No, I don't. Cumulative queries is a way of deciding, of asking the following questions. Instead of using one particular time step of some data and answering the question, what is the threshold of this particular scalar field, we ask questions like this. As a cumulation of time step, when does a particular condition happen? Okay, so it opens up a different set of queries that can be requested for a set of data. And let us decide after I finish this if you want to see the demonstration. I'm going to show you the enhanced display of ParaView, which are quite interesting. I believe I still have a VNC session running. I'm going to run ParaView. All right, something very simple. I'll get my standard I cannot get to it. So I'll use Python. Python. I don't think this will actually work. Wavelet. Oh, it does work like that, yeah. All right. I have a wavelet object, which I cannot display. Fine. I would show it. Here's my box. I will tetrahedralize it. Tetra tetrahedralize it. And I will shrink it. All right. So I have now a large number of objects. I can zoom on this. Not too much, though. There we go. It gets very difficult to see those objects. I will now load a particular plugin called the iDome Lighting View. I will create a new window called an iDome Lighting window. I will display the same data. I will link those two cameras. And then now I will let you judge the difference. Okay, this is the normal way of doing the display. And this is the other way. So this particular technique here does, sorry, I got too far, does a silhouette over all the objects to help with the depth perception of the field. So it's quite effective when we have a lot of very small objects in 3D where we lose perception of their position, etc. We use that particular plugin. So this is a nice GPU-based technique for rendering, which is a nice addition to ParaView. Let's do another example of a different plugin, which is called the Surface Leak plugin. We've discussed it this morning quickly. To use this, I need a vector field. So I'm going to create one. I will do a gradient. There we go. And I will do a slice through that gradient. All right. What am I showing? I'm showing the magnitude of a vector field. It's not very interesting. Using the surface leak, here's what I get. I get a very dense texture showing the direction of the vector field everywhere in space in a manner that is independent of the resolution of the grid. So this is very useful anywhere you want to show a vector field on a surface. Okay? It doesn't have to be a flat surface. It can be a curved surface in space. This is called the line integral convolution filter. It has been recently improved for version 4.1, so it works really extremely well now. What is missing here is to get actually the sense, the direction of flow on this vector field. So it can be augmented with streamlines or vector glyphs, but this is something very unique, again, to ParaView. So we have here a couple of examples, the iDome Lighting View and the line integral convolution, which are plugins that you can import into ParaView to do the job of visualizing vector fields. There. I'm using this quite successfully in fluid dynamics, as you could imagine, to show vector fields that are tangent to certain surfaces. It's quite a useful technique. Both of those techniques use the GPU. And this is why ParaView here has a strong edge, because it knows how to implement some of those OpenGL filters that work directly on the GPU. Now, I said OpenGL libraries. I didn't say CUDA or OpenSCC or OpenCL, etc. There are some efforts. There are actually 3 such efforts in the States to create CUDA-enabled or OpenSC libraries for visualization. It's work in progress. I was dreaming of showing it to you today, but it just wasn't robust enough to talk about it. But VTK Piston, which is the name of this toolkit, is for the first time included in the VTK 6.1 release. So you're welcome to try it. DAX, that's the name of it, DAX, is another toolkit which does some CUDA programming for some of those visualization filters. Let's just say that the visualization community is awakening to the possibility of doing GPU-based computing. These techniques are GPU rendering. It's a level of complication less than GPU computing. All right. Visit and ParaView are fancy applications. It might be too fancy for what you need. Or maybe it's everything except the one thing you actually need. There is the possibility to build custom application. I have a demo. I don't know if it's ready here on Eiger. It doesn't matter. I can explain like this orally. If you wanted to restrict your analysis to some very specific subset of tools and filters, you could build specific mini applications. So ParaView and Visit give you a framework, and there are a couple of examples which you can try to compile and test. It's the skeleton of an application. Inside of it, you have one rendering view, and then it's your responsibility to the functionality to add the pipeline that you are interested in. It's very actually often the case that people will do always the same thing with their data. It's a fixed set of features they are interested in. In that case, the pipeline is fixed. We can program it into a mini application, and this is good to do. Oftentimes, you will also need some Qt programming skills. This could be a limiting factor. You can get away with simply using the VTK Python interface, which I showed yesterday. You saw a certain difficulty in setting up, in knowing the names of objects, etc., of filters. It's not trivial, but it can be done. So this would be also typical of an example of help I could provide you in building mini applications for your data requirements. I'm talking here about reducing the features of visit in ParaView to a very small subset of tools. We can also add to the existing ParaView and visit. This is also the type of service I am trained to do. This can consist in adding a particular data interface. So you have data in a particular format, and this is part of a large project. It's difficult to change. We can go read directly the data formatted in your particular way. I have a lot of experience with this. I've done this for many, many years. I can perhaps help you with that. Then perhaps there is an algorithm. So that is a filter midway through the pipeline that you know you would like to implement. This can be benchmarked as a Python filter, and I can help you with that. Once we like the functionality of it, either we keep it like this, or we can implement that as a C++ filter. That would require compilation of the filter, and then it could be imported into the environments as plugins, just like we've seen in the previous case here.